Classical artificial intelligence is hitting a wall. The massive transformer architectures and large language models that dominated the early 2020s now require gigawatt-consuming data centers to deliver marginal improvements. The scaling laws of deep learning are bending toward a physical asymptote. More power, more hardware, diminishing returns. IBM just announced they're not waiting for it to break. They've officially slated 2026 as the year they will deliver the first definitive example of scientific quantum advantage, a quantum computer solving a real commercially relevant problem faster than any classical machine on Earth. Their current processor, Heron R2, runs 156 superconducting qubits at 99.5 to 99.7% 2-qubit gate fidelity, executing circuits of up to 7,500 operations. Their next system, Starling, targets 200 fully error-corrected logical qubits running 100 million quantum gates by 2029. And they've achieved a 90% reduction in physical qubit overhead using a new error correction architecture that rewrites the economics of fault tolerance. Meanwhile, Google's Willow chip proved that adding more physical qubits can exponentially decrease errors. Microsoft's Majorana 1 is chasing topological qubits with built-in hardware protection. China's Zhuchongji 3.0 is already solving logistics problems 100 million times faster than classical systems. And the global quantum hardware market is projected to hit $20.2 billion by 2030. The question is no longer whether quantum computers will surpass classical AI. The question is, which problems fall first, and who controls the machines when they do? IBM's Quantum Roadmap. IBM's quantum journey started with brute force. The 127-qubit Eagle in 2021, the 433-qubit Osprey in 2022, the 1,121-qubit Condor in 2023. Each generation added physical qubits, but raw qubit count alone doesn't solve the fundamental problem: noise. Every quantum operation introduces errors, and those errors multiply exponentially as circuits get deeper. So IBM pivoted. Instead of chasing bigger chips, they shifted entirely to gate fidelity, error mitigation, and modular scalability. The result is Heron R2, 156 superconducting qubits using tunable couplers to achieve a median 2-qubit gate fidelity between 99.5% and 99.7%, with an error per layered gate of just 1.97 times 10 to the negative 3. That precision allows reliable execution of circuits containing 5,000 to 7,500 operations, enough to start doing real science. But the real breakthrough is the architecture behind Starling, IBM's 2029 target. Starling will deliver 200 fully logical, error-corrected qubits capable of running 100 million quantum gates. It's built on quantum low-density parity check codes, specifically bivariate bicycle codes, that use long-range modular qubit connectivity through specialized C couplers and L couplers to encode logical qubits across far fewer physical qubits. The overhead reduction is massive, 90% fewer physical qubits than traditional surface codes, a tenfold efficiency gain that compresses the timeline to fault tolerance by years. Real-time error decoding is handled by a system called Relay BP, which processes errors 5 to 10 times more efficiently on standard hardware than previous approaches. After Starling comes BlueJay in 2033, 2,000 logical qubits executing 1 billion quantum operations. The full, fault-tolerant quantum computer, built on an architecture that didn't exist 3 years ago. What quantum advantage actually means? The industry throws around 3 terms that sound similar but mean completely different things. Quantum supremacy. Google claimed it in 2019 with their Sycamore processor. A quantum machine performed a specific mathematical calculation exponentially faster than a classical supercomputer. The catch: the calculation had 0 practical value. It was a proof of physics, not a proof of utility. Quantum utility. IBM proved this in 2023 with a landmark Nature paper. Using the 127-qubit Eagle processor, they simulated the behavior of a complex magnetic material, the Ising model, beyond what brute force classical approximations could achieve. The result was scientifically meaningful, but narrowly scoped. Quantum advantage is the threshold that changes everything. It's the moment a quantum computer solves a practical, commercially relevant problem faster, cheaper, or more accurately than any known classical method, not a contrived benchmark, a real problem that matters to real industries. IBM has officially targeted 2026 for the first demonstration, using a pre-fault tolerant quantum computer orchestrated alongside classical high-performance computing nodes in a hybrid architecture, where quantum kills classical AI. Classical AI, including every large language model and every AlphaFold variant, fundamentally guesses. When simulating molecular interactions, classical systems use heuristics and approximations trained on historical data. They estimate the behavior of electrons. Quantum computers don't estimate. They simulate quantum mechanical interactions natively, mapping subatomic states directly onto qubits without approximation. That native capability guarantees quantum will overtake classical AI in specific, massively valuable domains. Drug discovery and molecular simulation, modeling the exact ground state of complex molecular bonds, is classically intractable. McKinsey projects quantum chemistry simulations will unlock $200 to $500 billion in pharmaceutical value by 2035, moving the entire industry from approximation to deterministic simulation, materials science, next-generation battery chemistries, high-temperature superconductors, and efficient industrial catalysts like nitrogen fixation for fertilizers all depend on quantum chemistry that exceeds the memory capacity of any classical supercomputer. Optimization. Complex, multivariable problems in logistics, supply chain, and financial portfolio management scale exponentially, making classical brute force useless. IBM has already partnered with J.P. Morgan Chase to explore quantum approaches to portfolio optimization and cryptography. Shor's algorithm on a fault-tolerant machine breaks RSA encryption, threatening every digital system on the planet and demanding an immediate trillion-dollar pivot to quantum-safe standards. The Qiskit ecosystem. IBM isn't just building hardware, they're building the ecosystem that locks developers in. Qiskit is the most widely adopted quantum software development kit on the planet. Over 13 million downloads, more than 7,000 independent projects, and 69% of all quantum developers worldwide use it as their primary tool. The Qiskit transpiler prepares workloads 83 times faster than competing SDKs and generates circuits with 29% fewer 2-qubit gates, squeezing maximum performance out of noisy hardware. Through the IBM Quantum Network, enterprises and universities run workloads on utility-scale processors via the cloud. And critically, Qiskit is back-end agnostic. Code written for IBM hardware can execute on IonQ, Amazon Braket, Azure Quantum, and Quantinuum. IBM is positioning Qiskit as the universal language of quantum computing, regardless of who wins the hardware race. The competition. IBM isn't alone. Google's Willow chip, 105 superconducting qubits, became the first processor to demonstrate below-threshold error correction, proving that adding more physical qubits can exponentially decrease logical error rates. That's the fundamental physics of fault tolerance, validated in hardware. Microsoft is taking a radically different path. Majorana 1 uses an exotic material called a topoconductor to create topological qubits with built-in hardware noise protection. Funded partly by the DARPA US 2QC program, the approach promises a faster trajectory to 1 million qubits on a single chip, though the engineering remains highly experimental, and the 2018 TU Delft retraction still casts a long shadow. China's Zhuchangji 3.0, 105 superconducting qubits from the University of Science and Technology of China, has already demonstrated real-world optimization. In early 2025, Chinese researchers used it for drone swarm logistics optimization, claiming performance 100 million times faster than classical systems. Backed by an estimated $15 billion in state funding, China is a formidable peer competitor to every Western corporate effort. The US counters with the $278 billion CHIPS Act. The EU has launched a €1 billion quantum flagship. The UK has pledged £2.5 billion. The projected global quantum hardware market, $20.2 billion by 2030, growing at 41.8% annually. Why this is the end of the AI era. The phrase "end of the AI era" doesn't mean artificial intelligence dies. It means classical AI gets absorbed into something bigger. The transformer architectures that power every major language model are hitting an energy wall. Training runs consume megawatts, data centers draw gigawatts, and the returns are shrinking. More fundamentally, classical machine learning is inherently incapable of navigating Hilbert space, the complex mathematical realm required to calculate multivariable quantum states. For any problem that is fundamentally quantum mechanical, molecular simulation, protein folding beyond approximation, advanced materials discovery. Classical AI will always be an approximation engine. Quantum machine learning changes that equation. Algorithms like variational quantum eigensolvers and quantum neural networks use classical systems to manage data flow while offloading the exponentially complex mathematical lifting to quantum processors. The future is hybrid computing. Classical AI as the interface and orchestration layer, fault-tolerant quantum hardware as the true computational engine. IBM's entire 2026 roadmap is built around this hybrid model, pairing pre-fault-tolerant quantum processors with classical high-performance computing nodes to deliver advantage before full error correction even arrives. Skeptics argue that quantum error rates are still too high for broad consumer applications, and that classical AI will continue to dominate language processing, computer vision, and tasks where quantum hardware offers no theoretical speedup. They're right, for now. But for the domains that matter most to the future of science, medicine, and national security, the transition has already begun. What's at stake? The nation or corporation that achieves fault-tolerant quantum computing first gains a decisive advantage in cryptanalysis, drug development, materials science, and military optimization. Shor's algorithm on a scaled machine breaks RSA encryption and exposes every financial system, every classified communication, and every digital identity on Earth. That's why this is being treated as a matter of existential national security. China's $15 billion investment isn't academic curiosity, it's strategic positioning. The CHIPS Act isn't industrial policy, it's a defensive posture against a catastrophic technological deficit. And IBM's Dario Gil has stated plainly, the ability to demonstrate quantum advantage in the next 2 years is possible. IBM's Jay Gambetta is equally direct about the architecture. They now have a complete system that requires an order of magnitude fewer qubits than surface code approaches, making fault tolerance not just theoretically achievable but practically executable. Microsoft's Chetan Nayak puts the stakes even more bluntly. Whatever you're doing in the quantum space needs a path to 1,000,000 qubits. If it doesn't, you're not going to solve the transformative problems.